first morning session, we have four very wonderful speakers. First, I would like to introduce Osman Malik, who will tell us of structured sketching and tensor decomposition.
Thank you, and thanks for the invitation to present here today. So my title has changed a little bit if you've looked online. And so what I will do now is I will motivate this. First of all, I'll say a little bit about sketching and how it works in general, and then motivate this idea of structure sketching from the point of view that we're interested in, which is from tensors and sort of why it's useful for tensor decomposition. So, right, so probably this is, a lot of you already know this about tensors, but I'll go through it anyway, quickly. So the tensors are just going to be considered as multidimensional arrays. So a D-weight tensor is an array with D indices. And the point of decomposition is this for tensors is the same as it is for matrices. So we can use it for the same purposes. And here's our favorite, the CP decomposition, which writes a tensor as a sum of outer products. So this is, in some sense, similar to the singular value decomposition. And when it comes to computing the CP decomposition, this is, as we know, it's a hard problem to do. So we can think about it as an optimization problem. So over here, we have some tensor, some data tensor perhaps, that we want to decompose. And we've decided on a rank that we want to decompose it into. And that's the number of these components that we have out here, number of outer products. So the goal now becomes to choose the parameters in these outer products so that we minimize this residual. And the way that a lot of people do this is by alternating least squares. So in case you're unfamiliar, the idea here is to not minimize with respect to everything at the same time, but do first update a subset of the vectors of this set of red vectors over here. Then we update the next set of vectors, and then this last set of vectors that are pointing into the board. And then we repeat this over and over again. And the reason this is popular is that each of these turn out to be simple problems. So in fact, just linear least square problems. And the keyword here for our sketching discussion is that these are least square problems. So they're sort of good use cases for these sketching ideas. So let's now not think about tensors for a little while and only look at least squares. So this is kind of just a classical least square problem. We have this here is the sort of the right-hand side matrix. Here is the design matrix, and A is the thing we're trying to solve for. So a little bit poor notation on my part here. I'm calling a lot of things M, but M is the name of the design matrix here. And if it's little m by little n, then the cost of solving this using something like QR is mn squared. So the idea of sketching, are people familiar with randomized numerical linear algebra sketching? Just raise your hands if you heard about it. Okay, so about half. So this is, in general, I think, a very interesting area. It's been sort of worked on in the last couple of decades and in computer science and applied math. And the idea is essentially, can we make our computation faster or better in some way by introducing randomness into the computation? So in the case of least squares, this can look something like this. So we add this omega here, this red matrix, into the least square problem. And if we just ignore how to sort of do this product for now and just suppose that it's given to us, then it becomes just a smaller problem. And if omega has r rows, then this new cost of solving this problem is now rn squared. So if r is less than m, it becomes cheaper. So that's kind of one of the motivations for using the sketching idea in the case of a large least square problem, which might be a little bit too expensive to solve. So there's two questions now. One is, does this work and does it make sense? And I won't talk about that today, but the short answer is that there's a lot of people have done a lot of work on like proving that this makes sense and that by doing this you get a decent solution. So solving this here gives something that's a decent solution to the original problem, basically. The second question is, how do we do this? Because if you look at this for a little while, if this is just a dense matrix, then this multiplication here is more expensive than this original cost, so it doesn't necessarily make sense. So how do you do this, and how do you choose omega? And I'll say a little bit about that. So here's a list of choices you could make, and there's other things you could do as well. But this is kind of the most popular ones. So the classical choice is to choose these entries as Gaussian IID random variables. And that's one of those cases where this multiplication becomes too expensive. So in practice, you wouldn't actually do this for like any sort of speed gains, but it's interesting from like a theoretical point of view because it's nicer to analyze. So that's one choice. Then there's various other things, so like fast Johnson-Lindenstrauss transform-based methods that use fast Fourier transform or fast cosine transform to do this multiplication faster, and various sort of methods, the two ones at the bottom here, that choose this omega in such a way that it's more or less sparse, which means it can be applied in one way or another more efficiently than if it's a dense matrix. Okay, so now let's go back to tensors again. So here we have our least square problem. And in the case of tensors, it's not just any least square problem, but it's a least square problem where there is some kind of structure. So in the case of CP decomposition, this M matrix here looks like this. So it's a product of smaller matrices. And similarly for the Tucker decomposition, it's also a product of smaller matrices, only the kind of product here differs. And the definition is not important of the product, but the idea is that there is structure. And this would also be true if you did something like if you used ALS for, say, Tensor-Train or Tensor Ring, or if you had, for example, something more general like any network decomposition, you could kind of apply an alternating least square approach. And at the end of the day, would boil down to solving least square problems where these M matrices would have structure. It would be a little bit more intricate than these products, but it would still be there. So the question now becomes, if we have a problem like this, where we actually consider the fact that there is structure in the design matrix, is it appropriate to just put in one of these sketches that we would apply to an unstructured problem? Or can we do something better here in the sense that can we somehow adapt these sketches and maybe let them be composed of a lot of, many smaller components in such a way that it somehow matches the structure here, so that especially applying this sketch to this matrix here can be done efficiently. And there's other potential benefits as well. Like here, if we use a lot of smaller components, it can potentially require less randomness. If for some reason that's a bottleneck to like generate random numbers and things like that. Okay, so I'll talk about the Gaussian sketch and how we can make it structured. And so remember here that this is kind of the sort of the standard kind of sketch, right? Where all the entries in omega are appropriately scaled Gaussians. And here's our structure matrix. So this would be what it would look like for like CP decomposition of a three-way tensor. So now what you can do here, and there's many ways you could sort of make a structured version of a Gaussian sketch. And perhaps the simplest way is to, in this case, since this is composed of two matrices, you can compose a Gaussian sketch of two matrices as well. And then just sort of you do a Kronecker product and then a transpose to make sure that it matches the structure of this. And if you know sorry, I keep saying Kronecker product, but I mean to say Catrarau product for these. But it's column-wise Kronecker products. So if you know your Catrarau products, you know this expression here. So if this here is our sketching matrix, and this is the thing we apply it to, there's a nice and simple formula here, which means that, so this means that we can compute this by simply applying this omega C on directly to C. We can apply omega B to B, and then this here is just pointwise product. So this now it's a lot more efficient than if we were to do this thing up here, right? And so for these kind of sketches, you know, we can, I didn't talk about the theoretical guarantees and things you can get for these kind of sketching approaches in general, but there's proofs that you can prove kind of not as strong, but you can prove results for these kind of sketches as well, that you get like these kind of distance preservation things and subspace embedding and stuff like that you get for the standard Gaussian sketch. And there's also more sort of fancy variants of this where you can let the rows of omega be vectorized tensors with random course, where it's can be something like CP or Tensor-Train or Tensor Ring. So that's a line of work. And there's been more recent work by Linjian and Edgar on sort of even more advanced methods where you have tensor networks with Gaussian course that kind of replace this omega matrix. Okay, and so I'll also say a few words about this particular sketch. So this was what I called a hashing-based sketch a few slides back, and this is another example of a sketch that you can apply more efficiently than just if you were to use a Gaussian sketch. So now the omega takes a little bit of a special form here. So it's composed of two matrices where D is just diagonal with plus and minus ones along the diagonal that are IID random, so like Rademacher random variables. And P is a matrix with a single one per column, and its position is chosen uniformly at random. Okay, so, and yeah, this turns out to not be a Johnson-Linden stress transform, but it's a subspace embedding, which is sufficient for these kind of least squares problems. So this is, and this, you don't have to actually form this. If you were to apply it, you can sort of implicitly apply it to a matrix by thinking about the action of this matrix on another matrix. So then this tensor sketch is kind of a structured version of this. It's kind of analogous to what I showed on the previous slide when you made a structured version of the Gaussian sketch. But this is a little bit more intricate how it works, but the basic idea is the same, that you can, this is how you can, when you have this sketch here, when it's tensor sketch, you can kind of apply it through this magical formula where you have, but the point is that you just essentially do sketches on smaller matrices. So you again do something to C and something to B, and then this here is a magic formula that is explained in these papers. And there's other also more advanced versions of this that have been proposed somewhat recently. And so there's also these other kinds of sketches that I mentioned, so that have structured variants. So I mentioned the fast Johnson-Linden stress transform has structured variants that were developed specifically for doing tensor decomposition in the first place. So that kind of shows this close connection between structure sketching and tensor decomposition. There's also these sampling based. So this is what I mentioned earlier, is kind of very sparse styles of sketches. And these have also been sort of developed in a number of papers. And I'm not going to say more about that because Vivek will tell you more about that in a couple of talks. So he'll go through some of the recent work we've done on using sampling methods in which leverage structure for tensor problems. And I also want to advertise here this monograph that came out recently. So overall, if you're interested in numerical linear or randomized numerical linear algebra, I would recommend looking at this, especially if you're interested in this software perspective. So it's kind of going through a lot of the field and doing a survey and introducing some new results. And in particular, chapter 7 is about these kind of structure sketches. If you're interested at all, I would recommend taking a look there. Okay, so now I'll just very quickly just talk about a paper, one of my first paper, in fact, that I did in my PhD. And I just want to show an example of when these structure sketches were applied to a tensor decomposition problem. So in that paper, we considered the Tucker decomposition, and we saw several talks about this yesterday. So the idea is now it's similar to CP, but there's an additional core tensor here in the middle. And again, alternating these squares can be used here, and it's a nice method for doing this. So here I'm just sort of showing what the step looks like graphically in a figure, and then here is what the corresponding least square problem looks like. So the key thing to keep your eye on here is that this design matrix here always has this Kronecker structure that I mentioned earlier. So I'm just gonna not dwell for too long on this. I'm just gonna click through them, and you can see here that it's you can formulate all of these least square problems. Okay, so what we did here was to insert these tensor sketches that I discussed earlier, sort of into this problem. So apply tensor sketch to the sign matrix, and then to here's the reshaped tensor, and we get this kind of alternating least squares algorithm. And the results here, the key takeaway is basically that we can get good accuracy and good speed ups. So I think what we decomposed here was a tensor that had about 1 million non-zeros, and the target, the decomposition rank was 10, 10, 10, so Tucker rank 10. And here is kind of along the x-axis is the size of the dimension. So it was from 1,000 up to 1 million. And the solid red line is our method, and the accurate relative error is on the y-axis here. So basically we get competitive accuracy, but also better scaling than the competing methods. Okay. So to conclude, I think sketching is fascinating, especially when structure is introduced. And I think tensor decomposition is a very good application area for this, because you have this structure that arises naturally in the problems. And if you'd like to learn more about structure sketching or just randomized numerical linear algebra in general, I would recommend taking a look at chapter 7 here in this monograph. And so the point of this chapter was to basically be as comprehensive as possible and sort of try to collect all sort of what's out there currently on these structure sketches. So maybe another incentive to look at this, if you've done work on this, is to go there and see if we missed anything. And if we did, then send me an email and I'll try to include it there, because we're working on revising this. So it's another incentive to look at it. And Vivek will soon tell you about our more recent work on using these ideas, these kind of ideas of leveraging structure in the case of sampling-based algorithms for tensor algorithms. Okay, and yeah, feel free to send me an email if you have any questions, and I'm happy to take questions now. Thank you.
So you're picking the structure of the sketch to match the design matrix. Do you need to assume anything about the input tensor? And it seems like most of the computation will go into sketching that.
Yeah, that's a very good point. So, and so let's see, where is that slide? Okay, yes, I think this is good. So the question here is basically, this is nice, this is what I emphasized, and we can do this fast, but what about this? Because X does not have a structure if it's just some, say, a dense data tensor, and that's a very good point. So you have to, depending a little bit on which sketch you use. So in the case of this method, for example, the tensor sketch can be like, if this is a dense object, then the cost of applying it is the number of entries or number of non-zeros more generally. So this is now all of a sudden prohibitive. So the trick that we used here is that we only apply the sketch once at the start of the algorithm. So basically as a pre-processing step. So we computed this only once, and then we reused these sketching operators throughout the algorithm. So that's one way to alleviate that issue. But the drawback of that is that we lose the formal guarantees that I didn't talk about today, but so basically you shouldn't do that if you want the theory to hold, but in practice, it still works pretty well. So for this kind of sketch, that's one way to address that. And if it's a sparser sketch, so I guess I don't have a slide of this, but if it's a sampling-based sketch, where basically the impact of the sketch is to, and Vivek will tell you more about this, but the impact of the sketch then is to only choose a subset of the rows in the matrix you sketch. And in that case, for one application of the sketch, you only have to touch a subset or yeah, a subset of the entries in X each time. So for that particular sketch, so anything sampling based, you can potentially get away with actually applying it sort of a fresh, new, random sketch every time. So, so yeah, but that's definitely one of the shortcomings of this structure, that X is not typically structure, and then it's kind of, yeah, you have to figure out a trick or some way to get around that. Yeah, I think that's well understood for, I don't remember exactly what the results are, but for the case when so I think if I remember right, I think you can say that in the more sort of standard case when this is Gaussian, and maybe I should go back a little bit further. So like here, I think you can have, there's an upper bound you can say on, say, if you know the condition number of M, I think there's a nice upper bound on Gaussian times M. And then there's a big, I think there are results for other, I know there's for, say, count sketch, for example, and I think you can prove it for other things as well. It just gets a little bit harder for when it's non-Gaussian. But I think in general, they should be well conditioned in or not a lot worse than M, I should say. Thank you. Yeah, I think the structure scale stuff is really cool, I think.
Oh, okay. After 20. Oh, yeah. You will probably stand. Hopefully not. Are we on time, really? I believe we do actually. Okay. Yeah, good. Great. Well, I'm very happy to introduce our next speaker, Carmeliza Navasca, who will tell us of sampling methods for tensor decomposition.
Thank you. Thank you for the organizer for the invitation to give a talk. Today, I'm going to talk about sampling methods for tensor decomposition. Let's see. Okay. So I'm going to start off with, everyone knows what a tensor is, so I'm going to start with a tensor. And so I'm going to, this is a COVID tensor. This is, this is directly from the New York Times COVID database. And we also use the US Census data to create a infection density tensor. And so a third or one third order tensor is a represent the infection density for a state. So in this case, I think our study is like for New Jersey, which is the densest state in the US. Okay. So the other tensor, so a lot of you know more about this than I do. I just wanted to point out for weight tensors as kernels in convolution networks, there are these image convolution, and you can use tensor decomposition for that. And what happens is when you do that, you see this swamp. So I'm motivated by swamp. I'm like a swamp lady. And so, and here are my two collaborators. Deepak is currently my graduate student, and Raman is currently at Stillman College. Alabama. All right, so we've seen singular valley decomposition from the last talk and from all the other talks from yesterday. So I like CP, so I think of singular valley decomposition as the sum of rank 1 matrices. So for tensor decomposition, sum of rank 1 tensors are just outer product of these vectors. And the canonical polyadic decomposition is basically given a third order tensor. Can you decompose it or split it up into a product of rank 1 tensors? Okay, that's pretty straightforward. All right. And the probably the most well-known method for CP is the nonlinear least squares. So as we saw from the first talk, essentially you break it up into pieces to subproblems of simple linear least squares, and you could update. And then you could update the factor matrices subsequently, right? So that's the Gauss-Seidel updates, right? So, and again, so there are some drawbacks of ALS. So there's this thing called the swamp, I mentioned earlier. It's just a curve in a log error plot, characterized by the need for a high number of iteration, inducing a slowed convergence rate. So Mollenkamp studied this. He studied different types of swamp. This is called the transient swamp. There's also the terminal swamp, which is just, it's not flat like this, but it just slowly converges. I have an example in a later slide, what a terminal swamp is. And so we've used a lot of technique, I call it swamp draining algorithm, which are essentially regularized optimization problem. So there are some cases where, there are different types of swamps, different type of transient swamps. So when you're doing ALS, what happens sometimes is that your linear least squares becomes really flat and you don't have a unique solution. So what happens, it could stagnate like this, okay? Also, if you are doing symmetric tensor, you have a symmetric tensor and using ALS, is not really appropriate to do alternating least squares because they're not distinct factors. They're actually, if you have partial symmetry, your A and B might be the same, or B or C are the same, or you have a full symmetry would be A, B, and C. So ALS mathematically doesn't hold for that, but you can actually just use ALS to see if you get a solution. You can get a solution and sometimes your solution is completely off, right? So we kind of reformulated ALS, depending on what type of symmetry you have in your tensor, full or partial. Also ALS, when you're on ALS, you have no idea what the rank of the matrix is. And sometimes when you guess, you're gonna get a swamp. Like, so if there's a border rank of 2, but in the sequence of tensors are all has a rank of 3 and you want 2, you're gonna get a swamp. Okay, so we have some way to approximate rank for ALS, approximate the rank as well as reconstruct the tensor. And you will see this, that for higher order tensor, this is prevalent. You go to 4th, 5th, or 6th, you're gonna get a swamp, okay? So by the way, the swamp, this term swamp is from Burdick and Mitchell. I believe it's in 1994, so it goes all the way back. So some of you are not born yet. So anyways, so this is the regularized ALS. I just wanted to go quickly So there's an extra regularization there. So this is equivalent to these proximal optimization type problem. Okay. This is what happens when you have if you have symmetry in your tensor, you need to reformulate your ALS, right? Because the factors are no longer 3 linear least squares. One of them, if it's it's going to be a non-linear least square, so you need to factor that in. So now these sparse, I wanted to, because it's a sparse workshop, I needed to mention the sparse optimization in providing rank. It's basically when you do, so in SVD, we have the singular value pulled out, but in ALS, we tend to absorb that in the columns of the factor matrices. So for this, we pulled it back out and use the singular value, these values, to zero it out. So just do an L1 minimization on these singular values that we often absorb in the CP decomposition. Okay, so, and there's 2 versions. I'm not a gradient descent person. I'm an ALS person, so I wanted to replace the gradient descent with ALS plus the L1 minimization on the alpha. And it actually performs much better than the gradient descent. Okay. Okay, so this is what I really want to talk about today. So what I'm going to do instead, so these are the, okay, so we have the objective function for ALS, or CP decomposition, or for the objective function for the CP decomposition. And so you have 3 equivalent ones depending on how you matricize the tensor. And so what we did here is basically just take the gradient with respect to the sampled columns. Okay, so, and you could do that. And these are if you do that, when you do the calculation, these are the 3 equations you're going to get. All right. So then what you can do is separate it. So you can separate the sampled one and the one that you leave alone. Okay. And what you have is a normal equation. Okay. And so from there, so the algorithm is very simple. Basically you sample a column, how many you want, okay, or randomize it. And then basically do solve the normal least squares just specifically on those sampled cut-free rows. And you leave the rest alone. And that's it. So what's the advantage of this one? So this is the computational complexity. I think this is for the, this is just for one loop of the ALS. So your sampling size will be much smaller than the rank of the tensor. Then, it's, there's a significant decrease in the computational cost. Okay. And, all right, so how do you choose your sampling? So you can just sort of, randomize it. You want to take, maybe 2 at a time, or 1 at a time, or 3 at a time. So you can also randomize how many set of sample you want. Okay. And also, so the one thing we also use is to, perhaps you want it to be more adaptive. So maybe you start with 1. And then we can take this norm test, which is, since we have that gradient that we calculate in the beginning. So so in this case, we don't have, so I think we just did the gradient from 2 previous iterates, and sort of we measure that each time. So if it doesn't satisfy it, we add more samples, and then we continue from then on. Okay. So, and So again, this is an example of a numerical test between ALS and SMALS. So if there is a swamp in the ALS, the SMALS can alleviate that. So you see there's a little bit of a swamp in the SMALS as well, but in the right plot, it could actually, not exhibit swamp. Okay. And in general, the SMALS is going to be much faster than ALS, but then you have to compensate for the error, not usually as good as ALS. But if you just want an approximation, maybe you don't really care so much about the error, then I would use SMALS and then maybe stop the algorithm and then initialize your ALS to finish it off with a much better accuracy. So we did a little bit more testing on ALS. SMALS is if I only use one sample at a time, I'm only taking one sample and then I iterate. And then the randomized SMALS is then I could take any sample, number of sample per iteration. And then the add SMALS are adaptive. I think the other, they're not. So there are two types of adaptive. I think it's, I forget what's the second adaptive one. But so it performs okay if there is a swamp for ALS, then potentially it could beat it, could get out of that swamp. However, if ALS, there's no problem with ALS, sometimes it cannot beat ALS, right? So another thing is sometimes it also has its swamp, right? But for the, for adaptive one, it's in this problem you're seeing there's still, they're all swampy plots, but the adaptive one does fairly better than the other two. All right, so let's see. So we apply this technique for forecasting COVID-19 infection. So from that COVID tensor, we remove data. Suppose you want to predict a week ahead what would be the infection density. Again, this is just removing 20% of the missing data. And ALS still does well on this. So it's just to show that it could predict to 70% missing data. It does, it could predict the trend. At least it will say it's up or down, okay? Also, so here we had removed 100% of the last quarter data, and it did fairly well in predicting the COVID density for 1 quarter, which is about 3 months. It's pretty good. Okay. So what we also found is that if we had missing, so about 70% or 80% missing data, it could not detect new variants. So it could predict the ongoing variant. But if you had like 80% missing data, it could not predict, it doesn't have a good forecasting COVID infection for the new variants. So, which is good, which shows that if you have more data, it could actually predict the rise of the new variants. Okay. Oh, 5 minutes. Actually, I think this might be my last slide, and thank you. That's fine.
So I was wondering, for when you apply the L1 regularization to the singular values or the alphas, do you have, so this is to zero out some alphas, right? Or to, yeah. So do you still have to choose like the number of alphas to consider? So it's like make some sort of upper choice on how many single values to include, and then
Oh, yeah.
possibly.
So yeah, you have to have some kind of initial bound to begin with. And so what happens, it's sort of, as the algorithm goes through, it will zero out. And the rank is still the same. Let's say I start with 50. I will end with 50, but at the end, I'll just count the number of zeros. Is that,
Okay, so it's a pretty insensitive, so you can just make it consider a really large number, and then it'll just,
you'll zero out as you,
okay.
the criteria is not at the end.
Okay.
And then I just count. I
Okay.
guess we should fix the algorithm so that it tells you what the rank at the end, but we do look at the alpha. And then we'll see, okay, that's zero. It depends how you threshold.
Okay, cool, thank you.
Yeah, I have a question that for your sampling, does it work well for the symmetric tensor once you like randomly picking?
No, we haven't tested for the, you mean random tensor or symmetric? Or did you
Symmetric.
So you would have to reformulate it because this is again based on the gradient for distinct for a non no symmetry. But so you would just change the gradient. So you could reformulate, but this one is you can't apply you can't put in the symmetric tensor for now, but you just need to reformulate the gradient. Yeah.
Thank you.
So the swamping behavior, to me, suggests a strong coupling between the degrees of freedom and the different modes. How well would gradient-based methods work for these problems? Because it seems like once you take the Hessian information, of course, the Hessian is a bit, it probably has bad condition number, but there are tricks for doing this. Then it should,
So
it should get rid of the swamp, I would expect.
So for gradient descent, they don't have a swamp, but they have a zigzaggy thing going on.
Yeah.
Yeah.
Gradient descent, you'd need, it has problems.
Yeah, it has
Yeah,
problems
of
too.
course. So, but you basically need preconditioning. Yeah, without preconditioning, it's not going to work well. Or some sort of a interpolation. Yeah, some ad hoc tricks.
Yeah,
like
so I'm learning
Anderson.
this
Thanks.
workshop. Yes.
Swamping behavior. You mentioned this use of regularization. Can you say anything about how you're choosing the regularization term, or if it's very sensitive to that?
So I know for this one, this would remove the swamp. The recent so without the regularization, you will tend to have a swamp, but that specific swamp, it will only remove a specific swamp that sort of, for each linearly squares, you tend to have a flat objective function. And so you have many solutions. So it's choosing kind of the wrong one. That's why it's not moving, it's stagnant. So what this term does will just sort of make it sort of not flat, like just it's not quasi-convex, is it? But so it will choose one, and then it will get out of that regime. So it's good at getting out of that regime.
Very
Yeah.
good, thank you.
I don't know if I answered your question.
Well, I'm happy to introduce our next speaker, Linjian Ma, who will speak of efficient tensor network contraction algorithms.
Thank you. Yeah, good morning, everyone. So today I'm going to talk about efficient tensor network contraction algorithms. In this presentation, I'm going to introduce two approximate tensor network contraction algorithms that we developed recently. And this algorithm has been shown to be much more efficient than the previous work, and it will accelerate multiple problems, including statistical physics and also simulation of quantum algorithms. This is today's outline. At first, I'll give a brief introduction to tensors and also tensor network contractions. And then I'll talk about our first work that contains efficient contraction tree for the Tensor-Train based approximation algorithm. This is a joint work from with Cameron Ibrahim and also Ilya Safro from University of Delaware. And also, again, then I'm going to introduce another work that contains a flexible and also more efficient low rank approximation algorithm. So note that here the approximation refers to the low rank approximation. And the second one is a joint work with Matt Fishman and also Miles Stoudemire from Flatiron Institute. So tensor is a multidimensional array of data. And in this presentation, I'm going to use tensor diagram to visualize tensor. In the tensor diagram, a tensor can be visualized as a vector. Sorry, not a vector, vertex, and also the number of edges attached to the vertex represents the order of the tensor. We can also easily use the tensor diagram to visualize the tensor contraction. A tensor contraction is a generalization of the measurement multiplication by performing a reduction over specific dimensions. In the tensor diagram, a dimension is represented by an edge, and an edge is contracted if it has no open end. So here I show 3 examples. We can like visualize inner product, measurement multiplication, and also tensor times matrix as based on the tensor diagram. A tensor network is a group of tensors, and the tensor network contraction just explicitly evaluates the tensor network as a single tensor. So you can think of this one as a reverse direction of tensor decomposition. We can also visualize the tensor network as a undirected hypergraph that represents its contraction pattern. The contraction of a whole tensor network can be denoted or guided by a contraction tree. And the contraction tree is a rooted binary tree, and each leaf vertex in this rooted binary tree represents one tensor in the original tensor network, and also one intermediate vertex in the contraction tree is a contraction output of its children. So in the right diagram, I visualize both the tensor network that is in blue and also the contraction tree. So with different contraction tree, you can have different computational costs for the tensor network contraction. Finding the cost optimal contraction tree is a hard problem, and previous works use different heuristics to find that. Even if we are using the cost optimal contraction tree, contracting the whole tensor network accurately is still a hard problem. And this is because the cost has been proved to be exponential to the tree width of the tensor network graph. Tensor network contraction has multiple applications. One that is discussed recently is the quantum circuit simulation. So a quantum algorithm or quantum circuit can be viewed as a special tensor network, and running the whole quantum algorithm is equivalent to contracting the tensor network that represents such algorithm. And in statistical physics, we can use tensor network contraction to evaluate the partition function of some specific physical system that define on graphs. And also in computer science, a couple of constraint satisfaction problem can be viewed as a tensor network contraction. As I've mentioned, contracting a tensor network accurately can be very expensive. So previous works propose algorithms to approximate it. The approximation scheme is to is that every time we generate some intermediate tensor when we do contraction, we approximate the tensor or large size tensor as a low rank or bounded rank tensor network. And previous works consider different tensor network structures. One lines of work consider using Tensor-Train or matrix product state to approximate the large tensor. And the other line of work consider using general binary tree tensor network to do the approximation. Here, the Tensor-Train is a line, has a line structure, and it has actually an unbalanced binary tree structure. But there are still a couple of open questions. The first one is, how do we choose the contraction tree for such approximate contraction scheme? And the second one is, what kind of low rank approximation algorithm do we use in such algorithm? and I'll introduce our work that stress these problems. So this is the overview of the presentation. I'll first talk about algorithm with the efficient contraction tree for the tensor-train based algorithm. In this algorithm, we select the contraction tree by solving a linear ordering problem of the graph. And this linear ordering problem is used to minimize the edge crossings. I'll talk about the relation between the cost and also the edge crossings. And our algorithm has around 6 times speed up compared to the previous work on specific problems. In the other work, we introduced algorithm with a flexible and cost-efficient low-rank approximation algorithm. Previous algorithms use orthogonalization, which contains a sequence QR factorization to perform low-rank approximation. And in this algorithm, we use normal equations, and we will show that it is much more efficient. So next, I'll talk about our algorithm to accelerate tensor-train-based approximation. So in the tensor-train-based tensor network contraction, the main idea is that every time we have generate a intermediate tensor, we then just approximate that tensor as a boundary rank tensor train. So the most critical step in this scheme is then to contract 2 tensor trains into an output tensor train. To do that, the standard way is to use a sequence of adjacent swaps of tensor train dimensions to move the contracted dimension between 2 tensor trains into the center, and then use contractions to eliminate that contracted dimension to generate the output tensor train. And in the middle figure, I visualize this process. Here we have 2 tensor trains, or 2 MPS, MPS1 and MPS2, and they share one contracted dimension. So to contract these 2 tensor trains, we first use 2 adjacent swaps of dimensions to generate the middle diagram that the contracted dimensions, the tensor adjacent to contracted dimension is adjacent to each other. And then we perform a contraction to eliminate the contracted edge. So in this algorithm, the time-consuming one is the adjacent swap. And it also affects the accuracy. Since when we perform the adjacent swap, we also perform a low rank approximation. Otherwise, the rank will go up exponentially. So that the number of swaps is actually the one that we want to minimize. So to minimize the number of swaps, we have an observation that is the total number of swaps we need to perform in the approximation scheme will be lower bounded by a quantity called the convex crossing number of the input tensor network graph. So the convex crossing number is the number of edge crossings, the minimum number of edge crossings if we want to embed the graph into a line structure. So based on this observation, we propose an algorithm called a cat and go. This stands for contracting arbitrary tensor network with a global ordering. So to construct the contraction tree, our algorithm contains 2 steps. In the first step, we generate a linear ordering of vertices that has a minimum number of edge crossings. Then we construct the contraction tree on top of this ordering. Here, on top of means that we want the contraction tree to be constrained by this ordering. And the algorithm is visualized in the middle figure. Here, the example tensor network contains 6 vertices, and we first generate a linear ordering that contains 3 edge crossings, and then we construct the contraction tree on top of this ordering. So know that all the contraction trees constrained by this ordering will have the number of swaps that is equal to the edge crossing. So for this example, the number of swaps will be just equal to 3. Finding the optimal vertex ordering that minimizes the edge crossing is a very hard problem. And here we use a heuristic called recursive bisection to generate the ordering. Recursive bisection is a heuristic that is widely used in generating vertex ordering with different objectives. Once we get the vertex ordering, we then generate the contraction tree by using dynamic programming and minimizing some cost metrics. And here, due to the time limit, I skip the details about the dynamic programming algorithm. Okay, so here I show some experiments that compare our algorithm with the previous algorithms. So I look at the example that we want to fully contract the tensor network that has a 3D tensor network structure and also defined based on the Ising model. We compare with two previous algorithms. One is called sweep contractor, and the second one is called cat-n algorithm. And both algorithms are Tensor-Train based, and their algorithm, they choose the contraction tree either by doing it randomly or choose it based on the exact tensor network contraction tree solver. So in the figure, the left axis is the experiment time, and the y-axis is the relative error. So we really want the point to be at the bottom left corner. As we can see, our algorithm is much better than the previous works. To reach a relative error of 10 to the -8, we have a speed up of around 6 times. Here's another experimental results, and we use tensor network contraction to simulate quantum algorithm. So we consider the random quantum circuit, and the input quantum gate quantum state is defined on a 6x6 grid, so it is defined on 36 qubits, and we apply a sequence of random gates to the quantum gate. So we define a tensor network that is equivalent to getting the norm of the output quantum state. So this quantity will be trivially be 1 if we calculate everything accurately. But since we regard the tensor network contraction solver as a black box, it may not be able to find the accurate solution. As we can see in the figure, the previous algorithm does not find the accurate norm or accurate solution, but our algorithm is able to converge and can have much better results. Next, I'll talk about the other algorithm, that is the tensor network contraction with efficient low rank approximation algorithm. Here, let me first introduce the objective for this low rank approximation. Our goal in each step of approximation is to approximate a part of the tensor network, here is called B, as a low rank one. When we perform this low rank approximation, we also want to consider the remaining part of the network into the objective. And this remaining part is called the environment in the physical literature. And here is denoted as L. So this is actually a weighted low rank approximation problem. So previous work solved this problem by only consider a part of the environment, so a small size of environment L. This mainly solves minimize the local error rather than the global error. And also in terms of the efficiency, previous work solved this problem by first use a sequence of QR factorization to orthogonalize L, and then perform a rank R approximation. This algorithm has some efficiency issue when L is not a tree tensor network, since orthogonalizing a non-tree tensor network is very hard. In terms of efficiency, we propose to use normal equations to solve this weighted low rank approximation problem. Again, the orthogonalization-based algorithm will first perform a QR on this L and then do a rank R approximation. We propose to first compute the normal equations for this L times B, and then the solution is directly projecting the B to the rank R leading subspace of this normal equation. Both algorithms generate the same result if we don't consider the conditioning, although the normal equation-based conditioning is a little bit worse. For the case where L and B are just matrices, both algorithms have the same asymptotic cost. For the case where L is a tensor network and can contain, and is a non-tree tensor network, then the normal equation-based algorithm is much better in terms of the cost. And we are able to show that theoretically, the cost of the normal equation will be upper bounded by the orthogonalization-based algorithm in terms of the asymptotic cost. On top of this normal equation-based algorithm, we propose another scheme called partition contract that is able to flexibly use the environment. Different from the previous contraction algorithm that uses a complete contraction tree, partition contract uses a partial contraction tree. So the partial contraction tree, in the partial contraction tree, each leaf vertex represents one partition of the input tensor network. And also one intermediate vertex represents the contraction output of these input partitions. When we perform the contraction, we consider all the tensors in the input partitions as the environment. So that if the partition is larger, then the environment we use is larger, and we are minimizing the global error every time we perform the low rank approximation. So this gives the user a flexibility to have a balance between the efficiency and also the accuracy. So here's some experimental results on, again, contracting a tensor network defined on IC model. We compare partition contract with cat and go, our previous introduced algorithm, and also two standard algorithms. As we can see, the performance is much better than the previous work, and also is a little bit better than the cat and go algorithm. So here, as to partition contract, we select the environment size as I think equal to 5. So it's like a reasonable size that have a balance between the accuracy and efficiency. Again, this is the experimental result that to fully contract the tensor network that is defined on a random circuit. The performance of partition contract is again much better than the previous work, and can be also a little bit better than cat and go, since we are kind of choosing a environment size that is good. So here's the conclusion. We introduced two approximate tensor network contraction algorithms, cat and go that contains a new contraction tree algorithm, and also the partition contract that contains a new and efficient low rank approximation scheme. So both works are still on the draft, and we plan to release the draft soon. But they are currently in my part of my dissertation that is published like a couple of days ago. So if you want to look at, you can feel free to take this as a reference. And I also have some future work in terms of cat and go. One direction is to design heuristics that find efficient vertex orderings that minimize the edge crossings. And also in terms of partition contract, I didn't talk about how do we choose the partition, the partial contraction tree. And how to automate that is also one future direction. And I also would like to thank my collaborators, Cameron and Ilya from University of Delaware, and also my PhD advisor, Osman Malik. And also for partition contract, I would like to acknowledge my collaborators, Matt and Miles. And thank you, and this is my final slide. Yeah, thank you.
Nice talk. Would you comment on the resource requirements for the, I guess, cat and go? So it's faster, but oftentimes you want to actually minimize the size of the intermediates that you're generating as you contract.
Yeah, are you
How do
talking
they
about
compare?
the computing resource or?
Well, basically, yeah, the max memory of the intermediates, that would be also useful to know.
Yeah, so it depends on the rank you set in the approximate scheme. So based on my experience, all the experiments are done on my single laptop. So I think a rank of like 1K should be okay. So if it goes up to like the rank is too high, then it will go out of memory. Oh, okay. I see. I think in terms of memory should be comparable. Yeah.
Hi, Linjian. So I have a question about the swaps. So I think this is with the cat and go.
Yeah.
Are the swaps something that you have to do no matter what to do the contraction, or are they sort of an optimization to make the contraction more efficient?
So swap is something you have to do when you want to form the output MPS. Yeah, so take a look at this example. For example, if we don't do swaps, we have like no idea how to remove the contracted edge. Yeah. So this is kind of the standard way people do to like align the MPS so that they are able to form the new MPS.
Okay, so the question is, which swaps are you going to do? And then each swap involves an error that you need to select as well.
Yeah.
And how do you pick that error? Is that according to the problem, or?
So in general, what I do is I fix a upper bound of the rank, and if the rank is like more than that, I just do the truncation, and I measure the output error. Yeah.
matrices.
Yeah. Yeah. That's actually a good question. So I sometimes see that due to the normal equation, the final accuracy digits, I mean, I can get is a little bit worse, but that's usually not too much of the problem since I can still get like 10 to the minus 10 accuracy, but maybe higher is some problem. Yeah. So it's kind of trade-off between accuracy and efficiency. Yeah. Yeah. Thank you.
Great, so I'm very happy to introduce our last speaker of the morning. We have Vivek Bharadwaj, and he will tell us of leverage-based sampling algorithms for tensor decomposition problems.
Thank you. I have to give credit to Carmeliza and Osman for the lead up to this because it's going to make the first few slides of this go very quickly. So this talk is going to cover two works involving CP decomposition. The first one's going to appear at NeurIPS. The second one is under review. And the second part of this talk is something that is more, I guess, emerging extensions of this work, which involves CP decomposition to Tensor-Train decomposition. Okay, so by now, the story should be familiar. Our goal here is to compute the rank R CP decomposition of a given n-dimensional I times I sparse tensor. And we're going to focus here on very large sparse tensors, mode sizes, so the side lengths in the millions, moderate decomposition rank, at most a few hundred, but we're going to assume the non-zero counts that we're dealing with here are several billion. Okay, and the name of the game here is alternating these squares, so we're going to randomly initialize the factor matrices, which I'm going to call U1 through UN, and I'm going to iteratively optimize one factor at a time, keeping all but one factor constant. And the optimal value for factor matrix Vj is given by this linearly squared problem. So minimized with respect to x, ax minus b, where a has this form of a Cauchy-Rao product that's a column-wise canonical product, and b is a appropriate flattening of my data tensor that comes to the input. Okay, and as Osman mentioned, there's a kind of standard way to accelerate these types of problems. I'm going to call my sketching operator S, I believe we called it omega. The idea here is to apply this matrix S, which has far fewer rows than it has columns, to both the design and optimization matrix. And now this smaller system, which we solve with respect to X tilde, has far fewer rows. It's much computationally cheaper to solve. And the idea here is that we want the solution X tilde to the downsampled problem. When you plug it back into the original problem, it should have a residual within 1 plus epsilon, the true minimum residual, with high probability 1 minus delta. We're going to call this the epsilon delta guarantee. And now the question is, how do you pick the operator S? So often talk about Gaussian and tensor sketch operators. Here we're going to restrict S to be a sampling matrix. So the idea here is that we're going to select and reweight rows for both A and B. And the effect of the sampling operator, you can see it over here. I've drawn out what this linearly sparse problem looks like on the left side over there. And you can see if I solve this using the normal equations, the effect of the sketching operator is given by those shaded columns in the matrixized tensor and shaded rows in the Cauchy-Rao product. I'm selecting certain non-zeros from the tensor and corresponding rows from the Cauchy-Rao product, and this is how we get our computational speedup. Okay, so there's been some prior work in this space. So I think one of the earliest works that takes the sampling-based approach to ALS and decomposition is this work 2016 called SPALS. This samples rows according to, and I'll define this in just a second, what's called the approximate leverage score distribution on the design matrix A. And this actually works surprisingly well. But if you look at the theoretical guarantees you get from this, it's worst case exponential in the tensor dimension n to achieve those accuracy guarantees on the quality of each least square solved. There's been some follow-up work on this, which uses similar approximations, combining random sampling with deterministic sampling, practical improvements. Osman had a paper, I think about a year ago, that shows that you don't need to have this worst case exponential dependence. You can actually get this complexity down to polynomial in all the sort of relevant quantities to achieve those accuracy guarantees, but you still have an issue in that you're going to pay a cost that is linear in I, which is the tensor side length, for every single sample you draw. This is fine for small tensors, but in the case where we have large sparse tensors, this may be prohibitively large. So that's our goal. We're going to get this cost that is linear in I down to actually logarithmic in I. So we're going to propose a data structure, which I'm going to describe in a little bit more detail, that has runtime that is logarithmic in the height of the Cauchy-Rao product A and quadratic in the target rank R. The sample according to, and I'll define this in a second, what we call the leverage score distribution on A. This is going to let us get good guarantees on the quality of each downsampled least squares problem. And when you plug this into alternating least squares, you get something that has much lower asymptotic runtime than recent kind of methods to solve this. And we're going to show that it's very practical too. We're going to show that it scales to the cluster setting and decompose these very large tensors in a very small amount of time. Okay, so I teased this a little bit. What is this leverage score distribution? You can kind of think of this as a importance measure on the rows of the design matrix, which again, is the Cauchy-Rao product for us. The ith leverage score of A is given by the following. I take the ith row of A and multiply it by the pseudo inverse of the gram matrix of A. That's that middle term over there. And I multiply it by the ith row of A times both. I have a row vector times a matrix times a column vector. And this results in a scalar. Okay, so if I sample rows proportional to these leverage scores, and I take a number of samples, J, that is some multiple of R. I'm going to just say it's R times this maximum of two quantities. Let's just say it's R over epsilon delta. Then I achieve my accuracy guarantee on the quality of each least squares problem. Okay. Sounds simple, but of course it's never that simple. The problem is that these leverage scores are very expensive to compute. So let's take a typical problem example. Let's say that I is something like 10 million. So I have these very large side lengths for my tensor. And even as low as n equals 3, my matrix A is going to have 10 to the 21 rows. So you absolutely cannot sit there and compute all these leverage scores and then draw from the distribution. So what we're going to do instead, we're going to sample implicitly from the leverage score distribution by drawing a row from each one, U1 through UN. I'm going to return the Hadamard product of these things. Okay, I'm going to draw each row conditioned on prior draws. So let's let these variables HADS1 through HADSN be random variables for the index that I draw from each matrix. And let's assume that they jointly follow the leverage score distribution. What I want is the conditional distribution on some random variable, let's say HADS3, conditioned on the draws that I've already taken for HADS1 and HADS2. And there's a convenient form for this conditional distribution. Let's say that I want the probability that I choose index S3 from matrix U3. The probability that I select that index is going to be proportional to this generalized inner product of three quantities. And what this bracket notation just means is I have these three R by R matrices. I take their element-wise product, and then I sum up all the entries. The element-wise product is taken at the following three quantities. First, I have the Hadamard product rows that I've already sampled, the S1 and S2 rows of U1 and U2. I collect those into this green row vector over there. I have the row vector that I want the probability of sampling. That's S3, so that's the second relevant quantity. And then I have this matrix G greater than K. G greater than K is the Hadamard product of the gram matrices and matrices that I have yet to sample from. Hadamard product with the pseudo inverse of the gram matrix, well, the entire Cauchy-Rao product, which is this matrix over here. This is a lot of quantities here, but all you need to know is that this expression costs R squared to compute. That's sort of a Hadamard product of two things. And so I'm going to describe the key sampling primitive that we're going to use to sample efficiently from this distribution. Let's collect that expression that I showed you earlier into this vector Q of length I. And notice that you can't compute Q entirely and sort of obey the guarantees that we want. That would cost order I R squared per sample per mode, because this vector has length I and it's going to cost you R squared to compute each quantity. So how can we sample from a distribution if we're not even allowed to compute all of its entries? Well, here's what we're going to do. Let's assume for a second that we magically had all entries of Q sitting in memory. How would you actually sample from this discrete distribution? It's kind of a very well-studied problem with very efficient data structures. but I'm going to take a very naive approach to doing this, and that is the following. I'm going to choose a random real number in the interval 0 to 1, and then I'm going to I'm going to initialize a set of bins, I bins specifically, where the jth bin here has width qj. And then I'm going to find the containing bin I for this random field that I've drawn. You can think of this as throwing a ball into this set of variably sized bins and finding the bin that contains it. And this is equivalent to sampling from the distribution, and I formalize what containing bin means over there in terms of the future sum. Okay, so how do I actually find that containing bin? Well, I'm going to use this binary search to find that, and I'm going to truncate this binary search to log I over R levels. So how does this binary search work? Well, at the root, I'm going to branch right in this search to find the containing bin if the sum of everything from 0 to I over 2 of this vector Q is less than my random real draw that I've drawn. At level 2, assuming that I've gone this direction, I take the sum of everything to the left, and then take the sum of everything in this kind of subsegment, and I branch right if and only if this is less than R. Okay, and the key here is that I can compute these summations quickly if I cache a little bit of information at each node. So let's let some internal node B correspond to some interval of rows that I'm going to call S of E to E of E. Okay, so if I take the sum of the elements in this Q vector from J ranging from S of E to E of E, so that sum just goes straight into this generalized inner product, which is completely linear. And then I get this matrix that is a sum that is sort of a row subblock of each matrix UK ranging from S of E to E of E, transpose times itself. I'm going to call this kind of inner term here, I'm going to call this a partial gram matrix denoted by G of B. And the trick here is that we can compute and store G of B for each node B in my binary tree in this time order IR squared and storage space order IR. Remember that I truncated that binary tree. And I only have to recompute the cache quantities once per ALS round. So this is not asymptotically adding to the cost of alternating least squares. And once you have this, at each internal node, you can compute this quantity that I showed you earlier in order R squared time per node. That C inverse normalization constant, I can read that off the root. And then yes, at the leaves, I do need to spend order R cubed time to compute the remaining values of Q, but if you look at the paper, you can reduce this to order R squared log R. The complexity per sample turns out to be nr squared log I. We're doing R squared work at each internal node, summed over kind of all nodes along the path from the root to the leaf, and a little bit more work at the leaves, and sum this over all tensor nodes, and you get the final complexity. Now that's a lot of work. Is it actually efficient? Well, yes. So the trick here is that all the sampling can be converted into BLAS3 for the construction of this tree and BLAS2 for the sampling. Here I've shown what is the runtime to construct this sampling algorithm and draw 65K, roughly 65K samples. And you can see here that I just want to highlight even when each matrix has more than 10 million rows, and we have 3 matrices. This Cauchy-Rao product is massive. It takes us less than a third of a second to draw 65K samples, which we're pretty happy about. Things are, of course, quadratic in R. Of course, we can't avoid doing this R squared amount of work, and things are linear in N as we expect. Okay, so let's plug this in and actually decompose these large sparse tensors. These range in non-zero counts from 3.3 million to 4.7 billion non-zeros. Here on the x-axis, I have target rank, and on the y-axis, accuracy or fit. And you can see here that our method, which we call STSCP, is very closely replicating the fit achieved by non-randomized ALS. So it's achieving good accuracy, and at the same time, the fit is not degrading too much even as the target rank gets larger and larger. Whereas if you look at these approximation algorithms like CPA or LessLev, this approximation algorithm actually has its fit degrade quite a bit for a fixed sample count as you increase the target rank. And we show in the paper that even if you were to increase the sample count, you kind of incur a runtime deficit that doesn't help. Okay, and we also get high performance implementations of these two algorithms. It turns out you can kind of scale this up. And if you compare this to a well-optimized, non-randomized CP decomposition library, you get speedups of anywhere from 11 times. This is to compute the rank 100 decomposition of this Reddit tensor, which again has 4.7 billion non-zeros. And there are several tailored communication and computation optimizations that we did for this that you can read about. And in the remaining time, I just want to, I'm not sure how much time that I have left, but in the remaining couple of minutes, I'm just going to tease a little bit about how you can extend this to this binary tree caching trick to other forms of tensor decomposition. So let's look at the tensor-train decomposition. This tensor as a contraction of order 3 tensor cores. So J's core has these dimensions Rj by J plus Rj plus 1. And if you want the 232 entry of this tensor-train approximation, I grab the second element of this first list, the third element of this list of matrices, the second element of this list of column vectors, and take the sort of chain product of these things. And so this is a very compact representation of a tensor that in the worst case has I to the n elements. And if you kind of squint, you kind of have a list of elements that looks a little bit like CP decomposition. And the sort of simplest way that you can apply a similar trick to what we did in CP decomposition, if you were to do TT-ALS, if you were to optimize the TT approximation with respect to some given tensor, be it dense or sparse, using the same kind of alternating least squares trick. It turns out that you get a design matrix that involves a product of these cores, which have this canonical orthogonal form on the left and the right, taking their Kronecker products, and then you have a flattened version of this tensor that you are keeping non-constant. You're trying to solve for the optimal value, and then again you have a reshaped version of the target, the observation matrix. So it turns out you can apply the same kind of binary tree trick to the left and right matricizations, and I'm just giving you the theorem for the left matricization. There exists this data structure that costs you something like order IR cubed tensor-train core to build. That's asymptotically identical to the cost of orthonormalization to these cores. And for any j ranging from 1 through n, you can sample a row from this left subchain proportional to its squared row norm, which turns out to be equal to its leverage score in this case. This time j minus 1 r squared log I. This is identical to the cost to actually form that row. So in some sense, this is kind of as good as it gets because after you take these samples, you form the row itself. And you can accelerate TT-ALS using this approach. And I'll leave you with some ongoing work, which is that this is nice in that we can accelerate TT-ALS, but we're looking for further applications of this orthonormal tensor-train sketch. The extension to the non-orthonormal case is challenging, but potentially rewarding. So if you have an application involving contraction of an unstructured operator with a tensor-train or NPS, let's talk, because the sketching operator might be useful. So thanks. Yes. Yes. So here we're not adaptively varying the sample count. We just keep it fixed, j equals 2 to 16. So you can certainly layer this on top of strategies that vary the sample count. The idea is that you want to take more and more samples as you get closer and closer to convergence to improve the accuracy. But I think the idea is that we're keeping a fixed sample count just to ensure sort of a level playing field here. But even if you were to increase the sample count for the comparison methods, you end up incurring a runtime cost that sort of does not justify the increased samples you take. Yeah, I think it's especially at high rank, this effect becomes very manifest. I'd like to highlight this Enron tensor, I think is particularly ill-behaved, whereas if you keep the sample count constant, you actually see a degradation in the fit. Yeah.
So you're sampling according to the leverage scores of your factors, right?
Yes.
But if this is a sparse tensor, I can imagine sometimes the leverage scores of the of the factors may select constraints that are 0.
Yes, that is completely correct. So one thing is sometimes this is desirable. So once you run the algorithm for a little bit, you actually you want to capture the zeros as well as the non-zeros. So in our case, it's not the completion problem. 0 is really a true 0, and it will select 0 constraints, and that's fine. That is, I think, actually a feature, not a bug. Now, where this sort of becomes a bug is at the beginning of ALS. Because this tensor is so sparse and you basically have no prior information, you may get into a situation where you take a lot of 0 constraints at the beginning. And this does not violate any of our guarantees just because the solution to the least squares problem has very high residual at the beginning. So there's ways to get around this. One is to use something like a randomized rangefinder to extract a little bit of information from the sparse tensor beforehand. We did this for the Enron tensor, but we didn't have to do this with any of the other tensors. You could also just run a single round of non-randomized ALS and what sort of gets out of this ill-behaved portion of the loss, and then run the randomized algorithms that gets both conversions.
Okay. So I was asking particularly in regard to, I think, slide 8.
Yes.
You had a guarantee. Yeah, were you assuming something about B here?
No. So this is a guarantee that comes to you just by looking at the matrix A, which is kind of this.
Can you say more about how you sample in parallel, both building the tree and then?
Yeah. So it's a binary tree, which is the best thing in the world to parallelize. So in terms of construction, you can compute this partial Gram matrix for each of these leaves using symmetric rank K updates. So completely BLAS 3 construction. And then above this, it's basically an addition of the two children of each node. And this is actually a lower order term. So the construction is the higher order term is completely parallelized using BLAS 3 operations. And what we do is we chunk the tree up sort of by segments here, and we assign one processor to do construct each kind of the partial Gram matrices associated with each segment. So that's completely kind of parallel. There's no these threads don't step on each other's toes in any kind of way, no fault sharing or anything like that. To do the sampling at each stage, if you look at the quantity that needs to be computed, the major thing here is actually sort of a Hadamard product of GV with G greater than K, followed by a matrix vector multiplication. So what we do is, if we want to draw 65K samples, we march down the tree one level at a time. At each level, we perform a batch matrix vector multiplication. Now, at something like the root, you could actually make this a single matrix multiplication and sort of do batch matrix multiplication. We didn't see a huge speed up on the CPU side, but I think on the GPU side, that would actually be the trend.
And is there any load balance? Are the samples going to different clusters?
So in terms of load balance on a single node, there's no issue because we can sort of get these threads to kind of dynamically load balance, and each one is responsible for a single sample. So no load balance issues on a single node. On several nodes, it's kind of like pray for the best. There is no guarantee because leverage scores are highly known. Was there one more?
Just to follow up on Grace's question, so there's no dependence between the subsequent samples, basically, because you're sampling from the conditional distribution on the prior.
Yes. There is, in terms of load balance, is that?
Well, you're doing concurrent sampling now, right? When you do them parallel.
So we do each one at a. So we go through each of the modes one at a time, and for each sample, so we've sampled for each one all the way up to mode 1, and then we march down the tree one at a time, and then we move on to the third. So in this way that we kind of serialize each node. So
I see. So the kind of the dependence is only relative to the nodes.
Right. That's okay. It's still logarithmic.